Deepak sir, not able to. Yes, Deepak sir, are you there?
Yes, yes, sir. Yes, sir. I think is my screen visible now?
Yes, 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 yes. It's visible now. Maybe make it full screen, sir, so it is visible.
Yes, sir. I'll do it.
Okay, okay. Now it is perfectly fine, sir. Please go ahead.
Thank you. Okay. So, good evening to all. In this session, I'll be talking on a new topic, right? Retinal disease diagnosis using fundus images. Of course, we'll see the applications of deep learning algorithms, whatever we have discussed since last 2-3 days, right? So we've seen the advantages of deep learning algorithms over machine learning algorithms. Also, we have seen how to use deep learning algorithms, right? Uh, at the end, I will try to show you some demonstrations, right? I've received some requests from the participants to show you something, basically to demonstrate you something, right? So I've chosen actually tomorrow also I have a session there also I'll show you the demonstrations on segmentation. So today I have planned to show you, the demonstrations on the transfer learning which I discussed, even the attention mechanisms which I have discussed, right? So at the end of this session, right, I'll discuss, right? So we'll first discuss what are retinal diseases, right, and how to and what is the actually current process of diagnosing all those kind of diseases, and what is fundus image basically, because this seems very new to some of you, right? I don't know how many of you are working in this particular field. So I've actually made my slides as simple as possible so that everyone can understand what exactly this fundus image is and how this fundus imaging has become very popular. Although there are several other technologies we have, medical imaging technologies we have, so why fundus images is very, very popular and used for large scale screening of retinal disease. And there are also a couple of things, there are a couple of case studies which I have, right, which I would like to show you. I mean, there are a few studies which we have made since last couple of years. And we'll also see the applications of course, the kind of theories which we have discussed, like the attention mechanisms, the transfer learnings and all. And also I'll show you the different types of attention mechanisms which we have prepared to solve this kind of problem. So before we discuss what are retinal diseases and how they are diagnosed by the ophthalmologist and all manually, so let us also have a discussion on fundus, right? What is fundus and what is fundus imaging and how it is different from other types of medical imaging technologies basically used for eye disease like OCT and angiographs and all, and why it is so popular, and what are the biomarkers in the fundus images. Let us try to understand what do you mean by fundus first of all. The backside of the eye, right, is actually known as the fundus. The backside of the eye is actually known as the fundus, where the retina, the macula, fovea, choroid, and optic disc, as well as all these blood vessels you can see over here, these are all blood vessels, right, are located. Very, very important, right? The fundus imaging is very, very important, or the imaging or the projection of the fundus is very, very important to identify certain eye disease, right? You can see here is the optic nerve, and we can is the optic nerve which is connected to the brain, and this is how the projection of the fundus looks like. You now see, right? So this kind of image actually we are expecting from a camera, because from the normal camera, if you capture the photo from the outside, so this is not going to give us this kind of photo, right? So we need a specialized camera which can give us the projection of the backside of the eye, which is connected to the human brain, and most of the eye diseases, right, we easily identify it because this is where, as I mentioned, the retina, the optic corp, the optic disc, the blood vessels are located, right? So any disturbance to those kind of, right, regions is nothing but lead to some kind of disease we will discuss in detail later on. This is how actually the fundus images are captured through the cameras. Nowadays, even this fundus cameras can be equipped with the, I mean, they have become very portable. It can be equipped with even mobile cameras, right? And that is also going to give us something called as the projection of the fundus, which is nothing but the backside of the eye. So this is the output which we are getting from a fundus camera, right? And you can see this is, let's say, the human eye, and this is the machine, or you can say this is the fundus camera through which you can capture the projection of the fundus, right? And this is how the final fundus image looks like, where you can see this part is optic corp or optic disc. Sorry, this is optic corp and this is optic disc. And these are nothing but known as macula and fovea, which I will discuss later on. So as I mentioned, there are also different imaging modalities we have for the detection of the retinal disease. But fundus images are very, very popular because of its non-invasive nature, right? So fundus images are non-invasive. And at the same time, it is cost effective as well, right? So that is why fundus images are very, very popular compared to the other imaging or medical imaging modalities like OCT and angiographies, right? Although OCT and angiographies are having their own benefits, we'll also discuss at the end of the sessions that how to design something called as multimodal, or how to design a model that can consider different types of inputs of the same patient to have a better decision, right? We'll discuss in detail what is the meaning of multimodal and all at the end of the session. As I mentioned, because it is non-invasive and cost-effective, so it is suitable for large-scale screening. That is why it is currently being used in almost all the hospitals, or you can say the eye hospitals or research centers and all. There are several biomarkers, right, which you will find in the fundus images, which leads to, and the presence of such biomarkers leads to some kind of eye disease, right? So you can see here are some of the biomarkers of a typical fundus image, right? And these are basically, this is optic disc, this is optic corp. These are like optic nerves which are connected to the brain. So if there is any disturbance to this particular disc and corp, I'll talk about it later on. What do you mean by glaucoma? So glaucoma is a kind of eye disease, right? Which basically causes the damage to this optic corp or optic disc. We can call that damage to the which causes damage to the optic nerve, right? So any damage to this optic nerve windows, at that time the size is going to be changed, right? And the diameter is also going to be changed, right? I'll talk about it, what do you mean by CDR, like corp to disc ratio and all, and how this glaucoma is being detected manually, and what is, our task here. Fine. So, and there are also other biomarkers you can see over here, right? These are like soft exudates. These are like hard exudates. These are like hemorrhages, right? This part is particularly hemorrhages, right? So, and here is some of the microaneurysms, and basically these soft exudates, hard exudates, hemorrhages, and these microaneurysms, right? And the presence of these kind of abnormalities, right, leads to something called as diabetic retinopathy, a kind of disease, eye disease caused due to diabetes, right? We'll also discuss this problem in detail later on. What is diabetic retinopathy and what is the current status? What is the history, or you can say the statistics of diabetic retinopathy, and what kind of problem statement, right, we have in diabetic retinopathy diagnosis, right, and how it is being solved using deep learning algorithms. We'll see all these details, right, in a couple of minutes. Fine. There are also a few important areas like vessels, right? Vessels are very, very important, right? In retinal fundus imaging, you might have, if you are working in this area, so you might have, we can say, encountered something called as retinal vessel segmentation is one of the popular tasks, right? Which everyone needs to perform over the fundus images, right? So these are the blood vessels you can see over here, right? Sometimes even it is very difficult to identify, right? You can say the blood vessels and all properly through the naked eye, right? There are also several other biomarkers in fundus images, which leads to different types of diseases, right? So here are some of the, you can say, extensively used biomarkers for the detection of the glaucoma and diabetic retinopathy, for example. So retinal diseases, as we all know, that the major causes of blindness, or you can say partial or permanent vision loss across the globe. So there could be different type of retinal diseases, right? One is like glaucoma, very popular, diabetic retinopathy, as related macular degeneration, AMD, cataract, and myopia. There are several other diseases also. And these are like very popular disease, eye disease, you can say. So the statistics says that according to an estimation by World Health Organization in 2021, around 2.2 billion individuals suffer from visual impairment. And in India, the leading causes of blindness are due to cataract, might have heard about, right? Glaucoma and diabetic retinopathy. The most important thing, right? This number is really high, right? So this number is really high, but the most important thing that we can note down here is in most of the cases, this blindness in the people can be prevented if they are detected and treated early. That is very, very important. So early diagnosis and on-time treatment is very, very essential, right? So we need to create awareness among the individuals, right? Not only in our country, even across the globe, that always we need to go for regular eye checkups, right? Those who are suffering from diabetes and those who are having some family history and all. So, right? So, I mean, we should go for regular eye checkups and all because early detection is very, very important. And there are several diseases like glaucoma and all, right, which do not have even symptoms at the early stages, right? So, there are like salient things. So, we'll discuss in detail, right? Later on. So what is our goal is to, can we help the ophthalmologist in early detection of the eye diseases, right? Which can, of course, save the vision of many people. As we all know, that the manual interpretation process is something very difficult, even observer dependent. It always requires still supervision, and we do not have that many number of ophthalmologists in our country, right? Compared to the large number of patients we have, even you will not find always the experts, right? So that is one of the reason actually why we are looking at designing some sort of automated approaches to solve the problem, right? And to at least help the ophthalmologist, or you can say help the patients, right? At least for, I mean, so that we can recommend, right, the patients, or we can say you can suggest the patients to visit to the nearest eye hospitals as soon as possible if the model, or you can say if your application or your model is saying that yes, there is a chance, or there is of course a chance for an eye checkup right now. That is what is our main goal here. So we'll see how we can tackle all these problems, right? And because the images are it's not easy to understand for us, so we need of course the help of the ophthalmologist to level the image, to annotate the image for us, so that we can build the relationship between the image as well as the different regions we have. There are different type of tasks that have been proposed over the years for you can say for solving this problem, right? So the tasks are mainly divided into three different types, right? I'll discuss in detail later on. That is classification, segmentation, and synthesis and all. But if you go through the literature, right, you will find that the early contributions, especially made by the researchers, were based on these handcrafted feature extraction methods, right, which we already discussed, right? Like it is machine learning based systems people have designed where they have extracted some handcrafted features which are static in nature. We already discussed what is static feature engineering and all. And also we have talked about, right, the concerns, or you can say the limitations of those kind of approaches, right? Where the selection of an appropriate feature structure as well as a classification technique is always a concern. That is what we have also discussed, and the features are also static, and that is why we sometimes do not get good results, right? So we have seen all these things later on. Even the early days research on retinal disease diagnosis was based on machine learning approaches. Only later people have moved from machine learning to deep learning when this deep learning became very popular and all, right? So we'll see these things in detail and why this deep learning is very, very popular. We have already discussed the role of deep learning, the effectiveness of deep learning models over these machine learning models, right? And of course, we have also seen the properties of convolutional neural networks, what it does in the initial layers, what it does in the later layers. And also we have talked about the different ways to use especially convolutional neural networks, right? To solve medical image, including the fundus image analysis task, right? So we have seen that yes, either we can design our own convolutional neural network or deep learning approach. We can train it from the scratch. That is what we can do. Either we can adopt different types of transfer learning strategies, which we have discussed. It all depends upon the kind of data set you are dealing with, what is the size of the data set, whether it is large, whether it is small, and whether the source task on which the pre-trained model was initially trained and the target task is similar or dissimilar. That is what we have discussed. And the third one is again a part of the transfer learning where we can use a pre-trained architecture as a feature extractor to only extract the features from the pre-trained architectures like AlexNet, right? and then send the features, store the features in the feature vector, send the features to a classifier. That is what also we have discussed in the last session, or probably right on which was on transfer learning. I'll also show you the demonstrations on transfer learning today, right, by considering some of the data set. But if you want, you can also modify the data set, and you can also check the performance of the pre-trained models on a variety of, on a diverse set of data sets, I can say. So these are actually the three areas, or you can say three problem statement, which has been extensively, right, you can say solved by the researchers over the years using deep learning algorithms. One is the classification of the retinal disease. One is the segmentation of the regions, which are very, very important for analyzing the retinal disease. The third one is synthesis. There are also a couple of others, right? There are also a couple of others, but these three are very, very popular. Synthesis is like how to synthesize, right, the images, especially the fundus images, right, in case where the number of images are very limited to train a large model. In that case, what we can do is we can generate some synthetic or high resolution synthetic images or fundus images, and we can use the images, whatever we have in the training set, along with the synthetic images for training the whole model, right? We'll see later on some work on classification, segmentation, and synthesis you can relate with. There's a lecture, I think, on generative models, where you might have studied something called as variational autoencoder to the diffusion models. And in between, there's a very popular architecture known as generative adversarial networks and its several variants, right? So all these approaches have been explored, right? If you go through the literature, you will find how people have made synthesis on the retinal fundus images, right? So these are some of the architectures that have been explored, right, extensively for the synthesis of these retinal fundus images and all. Here is some of the statistics, little bit old, right? But which I've taken from this paper, which was published in Medical Image Analysis. Is one of the you can say a good journal in the field of medical imaging, right? So here you can see there is a survey actually from 2012 to 2019 that how many papers, right, have been published over the years from 2012 to 2019 on retinal image analysis, right? Of course, using deep learning. So you can see using deep learning, there were 12 papers were published on this particular area in 2019. Probably it is going to be even more than that if you consider, right, 2024 or 2025. Right, so that means the number of papers that have been published over the years is growing exponentially, right? Here is another statistics that how many papers have been published, based on different tasks. The task could be only retinal vessel segmentations. It could be on optic corp or optic disc locations or segmentations. Could be on diabetic retinopathy detection, or you can say grading, right? It could be on glaucoma. It could be on cataract. It could be on AMD, and there are several other diseases as I mentioned, right? So the synthesis you can see over here is 7%, 7.7% of the work on image synthesis, which we discussed, right? So you can see diabetic retinopathy is such an area which has been studied extensively, including the retinal vessel segmentation, as I mentioned earlier. And there are also a few works on glaucoma, very, very important, a very common disease. We'll also discuss in detail, right, what is glaucoma and how it is being detected and what is the cause behind this kind of disease. Okay, and cataract also there are less number of works. And there are also a couple of works right now going on, right? That is surgical fundus image analysis and all, right? We'll discuss later on. Now we'll see some of the case studies. I mean, especially I'm trying to focus on some of the diseases, right? Like glaucoma and diabetic retinopathy, which I have chosen. Right? We'll start with glaucoma detection using fundus images, and then we will see what are the multiple stage, we can say multi-stage glaucoma detection, right? Why do we need to detect glaucoma at different stages, right? That's the part actually which I'd like to highlight in this particular session. So we'll start with glaucoma. What is the glaucoma? It is a common type of eye disease that leads to optic nerve damage. You can see over here, and ultimately resulting in irreversible and permanent vision loss. It is basically caused due to the excessive pressure inside the eye, right? Which we call it as an intraocular pressure. And that is why actually, and because of this pressure, right, I'll discuss, right, and how actually this pressure is built inside the eye and how it progressively damages the optic nerve. I'll discuss that situation in another slide. Now, if you look at the statistics, around 64.3 million individuals aged 40 to 80 years, right? So glaucoma, right, has many patients, right? So over 40 or over 50 years. So in 2012, the statistic says that around 60 by 2040. It's really a high number. And now also let us look at the vision, the impact of the vision loss at the different stages of the glaucoma. This is through the normal eye. This is, right, the vision loss, or you can see the impact of the vision loss, right? You can see the vision field over here is getting reduced. And this is sometimes known as early stage glaucoma. And it is advanced stage and will be completely black out, right? Even, right, when the person is at the advanced stage or the severe stage of the glaucoma. There's a severe stage also. It will be completely black out. And it is an irreversible disease, right? So therefore, early detection of glaucoma is very, very important to save the vision. And we look at the statistics, right? The number of persons or individuals that are being who are being affected, right, by glaucoma is really high. So we need to detect this particular disease at an early stage. So how it is currently being detected? So it is currently being detected with the help of something called as, of course, fundus images. And the biomarker in this case is something known as COP to disc ratio, right? And one of the most important thing, right, which we should know in case of glaucoma, that majority of the glaucoma patients experience no noticeable symptoms during the initial stages. This is actually the major problem, right? There will be no such symptoms, right? The glaucoma patients find at the initial stages. And that is why it is challenging to detect glaucoma in the initial stages. But if it is detected in the initial stages, then only it can be prevented. So then how to detect and what are the, right, you can say gold standard metrics that are being used for glaucoma, right? One is COP to disc ratio, which is very, very important to understand. And any escalation to this value, right, which is in between always 0 to 1, I will discuss, right? Any escalation, right, of the CDR score is regarded as an indicator for this identification of the glaucoma. So what we usually do here, what basically and how it is being detected. So before I discuss how it is being detected, what are the biomarkers and the clinical features to detect glaucoma, what is basically the CDR and what is the range of the CDR values for early stage and for advanced stage and for severe and all. So let us also discuss what causes glaucoma. Right? As I already mentioned that it is glaucoma is only because of the excessive pressure inside the eye, which basically damages the optic nerve. Now there is a question why there is a pressure in the eye, right? So you can see the image which is there in the left hand side is nothing but a normal eye. The pressure is also normal inside the eye, but the image in the right hand side is something very different. Our eye always produces a fluid called aqueous humor. This fluid, right? It always produces the fluid which is known as aqueous humor that nourishes our eye. And this fluid basically drains out through a mace-like structure which is known as tubercular. Right? This particular fluid used to always drains out using through this tubercular mesh work, right? But sometimes these particular liquids, right, or you can say this aqueous humor gets blocked, right, because of this particular. I mean, it sometimes gets blocked, and if it is blocked, then this particular fluid creates pressures inside the eye and ultimately damage the optic nerve, right? And then we get a different shape of the optic cup and optic disc, and that is why, right, these are the major indicators to identify the glaucoma disease, right? Because of the pressure which is built due to this particular liquid is blocked. I hope it is clear. That means the fluid, right, normally drains out. It normally drains out, right, through this particular mesh-like structure known as tubercular meshwork, but it is sometimes also blocked, right? And because of this reason, there is a pressure built up inside the eye, and that is why actually it damages the optic nerve, which is connected to the brain, and sometimes also, right, the patients lose the vision because of this. And this process, sorry, this can be captured, right, through the fundus camera, or you can say the fundus images, which is nothing but optic cop and optic disc. Now you can see here are two fundus images we have. One is for normal, one is actually taken from a normal patient, one is taken from a glaucomatous patient, right? That means the person who is having glaucoma. You can see over here, because we are interested in this particular region, and this particular region is nothing but actually the optic nerve region, and which is now looking like two different parts. One is like optic cup, this is optic cup, and this outer circle is nothing but optic disc. So what exactly these ophthalmologists do here is to identify the glaucoma is nothing but they used to first identify the vertical diameter, right, of this optic disc and then optic cup. Then they used to find out the ratio between, right, the ratio between the optic cup and optic disc. There's a cup to disc ratio, right? So you need to first identify the vertical diameter, you can see over here. And then you need to also identify the vertical diameter of the optic disc and then take the ratio between them, right? And if the ratio is beyond 0.5, then you can call it as an early. It is purely manual, right? It's purely manual. You need to first identify the region where especially this optic cup and optic disc is located. And then you need to identify the diameters of the both. And then you need to check the ratio. If the ratio is beyond 0.5, and then it is early stage glaucoma. If it is greater than 0.8, right? This is known as a cup to disc ratio. So then if it is 0.8, we can call it the advanced stage person. So if it is close to 1, then it is a severe stage glaucoma, like that. This process is purely manual, right? It is sometimes difficult even to identify the cup and the disc separately, right? Even through the naked eye. Even for the experts, it is sometimes very difficult to identify. So that is why we need, some sort of algorithms, especially, those intelligent algorithms through which you can detect whether, right, or you can analyze these images and ultimately end up with something that yes, this particular image contains something which is related to glaucoma disease and all, right? So there are a couple of tasks here people have solved related to glaucoma. One task could be the classification. One task here is like the classification whether this fundus image carries glaucoma or not. That is one of the tasks which is known as a binary task or binary classification task, I can call it as, where given any image, whether it is left eye image or right eye image, you need to check that whether that image contains glaucomatous eyes or not. That is a binary classification task. I mean, for an image, we need to assign a label, whether it is normal or abnormal, that is like normal or glucomatous. The second one could be a multi-stage classification, which is very, very important. We have been working on this particular problem statement since last 5 6 years, 6 years probably, right? So I've spent a lot of time even with the doctors, right, to especially the ophthalmologist, right, to decide that what kind of problems actually we should solve. And initially, actually, we were focusing on solving this binary classification problem, where our task is to collect the fundus images from the hospitals, then train the model, and the model will tell that whether the image belongs to normal category or glucomatous category. But later, when we talk to the ophthalmologist, then ophthalmologist also used to say that yes, multi-stage glaucoma detection is really very, very important, which is a case very close to the real-time scenario. So can you solve this kind of problems? But the only problem here is that getting an annotations of those multi-stage data is not it is really a difficult task even for the ophthalmologist, right? We don't have even such kind of data set in our country, but fortunately we have got few data sets from other hospitals, which is publicly available. And also, I mean, we are in the process of collecting few, or you can say samples, right, with in collaboration with some of the hospitals and all, to validate our approach. The ultimate goal, whatever the model we have designed, yes, we have got a better performance compared to the state of the art models, that is fine. But what is the most important thing is nothing but whether we have validated our approach on the real-time data or not. And that is what we are doing right now, right? So I'll discuss in detail what is this multi-stage classification. We have already seen there are multiple stages. There could be multiple stages, right? It's very, very important, right? Stage detection in case of glaucoma is really a very important task. Whether it is early stage, moderate stage, advanced stage, severe stage, those are like very, very important to identify, and sometimes even very, very difficult task compared to the binary classification we will discuss in later. Why this multi-stage is more challenging compared to binary classification task. And there's also one more task related to glaucoma is like optic disc and optic cop segmentation. You need to first highlight the region along the boundaries of this optic cop and optic disc, right? So basically, you need to first locate where exactly this optic cop and optic disc is, and then you need to provide the boundaries of the optic cop and optic disc, right? So that is what is the task of optic cop and optic segmentation, optic cop and optic disc segmentation, which is also a very popular task, right? In case of glaucoma diagnosis and all. Fine. To this end, we have, as I mentioned, developed a couple of approaches, right? Initially, we developed few approaches for binary classifications, where the task is very simple. You can see over here is an input fundus image, and the output is like whether it is normal or glaucoma, like this. And this is one of the architectures which I think proposed in 2023, as to remember. So it was published in 2024 as a journal, Engineering Applications of Artificial Intelligence. And our main goal here was to design something called as our own model, convolutional neural network model, right? Without using any pre-trained architecture and all. And the goal was to also design a lightweight approach, right? So, and then at the same time, what actually, if you look at this particular architecture, I'm not going into the details of these architectures. If you want, so you can go through this paper, you'll get all the details. Even the codes are available, right? So you can also go through the code and all. Fine. So, but I'll just tell you what was our idea actually that time, and to actually solve this particular problem. So the idea was just to propose one something called as multi-scale feature representation block. That this is what is the block for feature extraction we have proposed. Like there are several blocks you might have heard about, like residual block, dense block, and all. But this block is something very different from them. And you can see over here. So what we have done is we are applying sometimes a sequence of the 3x3 filters. Sometimes we are applying a single 3x3 filter. But the idea was something very different. And the idea was just to increase the receptive field size and ultimately analyze the features at different scales. And instead of applying 2 3x3 filter, is have the same impact of applying 5x5 filter, right? But we are not using 5x5 filter because this 5x5 filter leads to more number of parameters compared to two sequence 3x3 filter, right? And depth is again going to be high in case of you can say 2 3x3 filter. That is just one of the ideas which I'm talking about, right? So you can also discuss if you're having any queries at the end, so you can also write chart works, and I can also discuss in detail, right? So why do actually we have taken two sequential 3x3, and what is this particularly, and why we are interested in multi-scale feature representation, because we want our models would analyze the features at different scales, because the kind of pathological regions we have, like whether it is optic curve and optic disc, that varies right rapidly in shape and size. So that is why we thought of introducing something called the multi-scale feature representation block. And every multi-scale feature representation block here is followed by an attention mechanism, right? So attention mechanism. So in this attention mechanism, we are calling it as a channel supple dual attention mechanism, where you can also find the application of both channel attention and spatial attention. There is a channel supple unit as well here, right? So this ultimately helps in enriching the feature learning capability of the model, right? And this model has been trained from the scratch, because this is the model which we have proposed. It is not a pre-trained model, right? And here is the details of the attention mechanism which we have proposed. I think in the last session we have discussed the different types of attention mechanisms, right? Where we talked about channel attention, we talked about spatial attention, right? So here also we have applied the channel attention and spatial attention, but the arrangement is something very different. And you can, if you want to just go through it, you can see this part is actually channel attention, this part is spatial attention, and this part is the channel support, right? And all these outputs are finally added element wise, right? And we have taken the average of it, and finally what we are getting is nothing but a feature representation of this f input, which is a final over here, right? And the size, actually the tensor size is again going to be the same, but we have highlighted the important channels as well as the important positions within this feature map, and that is why we are calling it as attention map, or you can say attention feature map, right? Fine. And here is all the results of which we have obtained, and we have compared with some of the pre-trained models which you might have seen. We have also discussed about all these architectures earlier, right? And these last two are like our approaches. Like this one is without the attention. You can see the results, right? Without attention. So with attention, of course, there is a little bit increase in the parameters from 1.7 to 1.9, but there's also an improvement in the performance, right? So there's also improvement of the performance. So there is a trade-off here. I mean, in between this, you can say the performance as well as the number of parameters as well, right? So I mean, basically, this kind of attention mechanisms have been introduced with all the feature learning blocks, and that ultimately introduced 0.2 million parameters, right? Which is 0.2 million parameters more than the previous one, but the result is really better compared to the first one, right? So that means, of course, these attention mechanisms are really helping to improve the performance, although there is a slight increase in the parameters, right? That was the main motivation here. And also we have compared with some of the state-of-the-art attention mechanisms like squeeze and excitation we discussed. CBAM, I think we discussed. There's a BAM, there's a global context attention mechanism. There's something called as a global attention block, which is like very close to this concept of the CBAM and all. So I'll also show you the demonstration. In the demonstration, I'll show you one of the implementations of these attention mechanisms and how do we implement these attention mechanisms. How do we, create the weights and then make it learnable, and then how these weights are going to be helpful in getting this attention map and all. Fine. So there is also a very popular attention mechanism called rotate to attend. We have compared with all these techniques, right? The state-of-the-art attention mechanisms. And if you go through the results, right, whatever we have reported in our paper and all, so that says that yes, our approach is really giving better performance compared to the other kind of attention mechanisms we have. But still, the kind of data sets which we have used in this case have been collected actually from a hospital, which is Kasturba Medical College, India. And then we have some collaborations with them, and we've got the samples from them, and it is, but still it is a binary class classification problem. And when we applied actually these kind of approaches on the multi-stage, which is really important, the accuracy actually degraded. That means we have not got actually this kind of results. There is a difference between, right, you can say there's a 10% difference in the accuracy when it is directly being applied to the, without fine tuning I'm talking about, right? So directly being applied to the multi-stage glaucoma diagnosis problem, right? So I'll also show you, we have already discussed about the importance of this multi-stage glaucoma detection and all. We have also seen this particular picture where, basically we are trying to highlight the impact of the vision loss at the different stages of the glaucoma, right? So we have different stages like early stage, advanced stage. Unfortunately, we do not have any data set available, which also covers other types of stages like moderate, severe, right? So these are also stages which are missing in the data sets, whatever is available till date, right? But we can also consider this kind of things, right, to design the, we can say the whole setup of this glaucoma stage classification. Here is three samples which are collected from the data sets, which we are actually considering for validating our model, right? For this is the case where there is no disease, there is no glaucoma disease. This is a case where the patient is suffering from early stage glaucoma, and here is advanced. I've intentionally chosen such samples where you will find drastic change in between actually different classes, especially different stages, you can say. But sometimes it is very, very difficult to identify the difference between the early stage and the normal, right? And sometimes it is even in between early stage and advanced stage, right? So there'll be actually huge similarities among these stages. We call it as interstage similarities. And this sometimes creates problems in accurately classifying the images into early stage or advanced stage compared to the normal stage, right? At the same time, there are a lot of redundant informations that you may find in the image. So these are like the images which has been first initially this particular portions have been identified, especially this optic cup and the optic disc region, right? And these are like some of the ROI images, right? The original images which you've already seen, and these portions have been detected. And then these are like the ROI images, which are really important for this classification of the glaucoma, the detection of the glaucoma. Fine. So I hope at least you got the idea that what exactly and why this multi-stage glaucoma classification is challenging compared to the binary classification task which we did earlier, where your task is to given a set of images. Your task is to only say this is normal and these are all like abnormal, right? So that is, a pretty, you can say, comparatively easier task than this multi-stage glaucoma stage, where you will find a huge similarities among the stages, and there will be very small lesion size and shape variations, especially COP and optic disc lesion size variations you will find, right, while solving the problem. So how to tackle all those problems and how to deal with those kind of problems, right? So we of introducing something called as a cascaded, attention-based network, and this is a work I think we did 2 years back, right? So where actually we have basically proposed something called as a novel cascaded attention-based network for multi-stage glaucoma classification, and that was published in IEEE Transaction Instrumentation and Measurement. Fine. If you look at the architecture which we proposed, so first the input image, the fundus image is passed through a backbone CNN architecture. And this backbone CNN architecture is nothing. It could be densinet, it could be resinet, it could be any backbone architecture which you can consider, from where you can get a high-level feature map. And that high-level feature map is further refined through this cascaded attention block which we have proposed. And this cascaded attention block mainly consists of two components. One is the triplet channel attention block. You might have seen that this kind of channel attentions, right? Like which is where the weights are 1D, which we already discussed, right? But what we have introduced here is the cross dimension channel attention mechanisms, and we have just combined the results of all these channel attention mechanisms, right, via weighted addition, right? And then whatever we're getting, right, is nothing but the final attention feature map along the channel dimension, right? So then followed by a spatial, the spatial channel attention block, which further helps in focusing on the important spatial positions, right? This is what is the channel attention. This is what is the attention mechanism. We called it as a cascaded attention mechanism, which we proposed and integrated as a plug and play module with any backbone network. And what we have got is very interesting results, right? So here is the detail of the attention block which I have discussed. Although I already mentioned that yes, the weights in case of channel attention is 1D. These are the weights, right, which is multiplied again with the input. You know that, right? It can be multiplied with the input element wise to get the output. So, but we are not only considering this one-dimensional channel weights, we are also considering two-dimensional channel weight, where we are trying to basically find out the relationship of the channel, which is k, with the height and with the width, as well as with the height, right? So that is what we are trying to do here. That is why the name is so-called cross-dimension dependencies or feature dependencies, right? Between the channel and width, with the channel and the height, and that also gives you some of the important informations, right? Important feature informations, and ultimately, whatever the output we are getting after this weighted addition, we're passing that output to the spatial attention block. We can see over here, which we have already discussed, and then the final feature or attention feature maps are here, right? Very interesting results which you have got. Please go through our paper, right, to know the more details about this. The, you can say, the motivation, and you can say the proposed approach like CNET and all. So here is one of the here is some of the results which we have obtained on two different data sets. Here is like Harvard data sets, which is available. Here is a data set actually which we have created by combining different similar type of data sets, which is a little bit bigger than this kind of data set which is available already, right? And here you can see the results in results of the proposed cascaded attention module compared to the triplet attention, the gap, the GC, the CBAM, BAM, and AC. These are like the state-of-the-art attention mechanisms which we have, where you can see completely that, yes, of course, the performance, whatever we are getting, is really right superior compared to the others. But you can see the number of parameters are either the same, right, and sometimes even it is lesser than some of the attention mechanisms that are very popular in the literature, you will find. And there are also few you can say attention mechanisms which do not contain much of the parameters, right, which contains even less number of parameters, but here the actual parameter is high, the performance is also high, right? So there's a trade-off again here. So of course, even the number of parameter, you can say the parameter increase is not significant here, right? So it is from 7.1 to 7.3. That is manageable. So if you go through the literature, also you will find there are a couple of other types of contributions made in recent years for the glaucoma stage classification, right? But especially we have also developed several other types of approaches, right? Several other types of approaches for glaucoma stage classifications. So here is one of the work, right? And if you want, you can just go through it, right? I don't have much time to go through all these details and all, right? I mean, what I'm trying to say here is one of the work which we have made recently, right? Where we have introduced something called as a fuzzy joint attention block, right? So I mean, we have also introduced a fuzzy concept to actually deal with the uncertainty that is present within the what I can say the feature. I mean, feature map, of course, whatever we are learning from the retinal fundus images, right? So if you want, you can just go through it. So this is with my PhD scholar, right? I must acknowledge him, Deepankar Das, so who is currently working in this problem statement, right? So here is actually the proposed attention mechanism which we have proposed, right? So if you want, please go through this attention mechanism. This is really a very interesting attention mechanism which we have proposed, where you can see different types of channel mechanisms. It is one is like local, which we have already seen. There's something called as a global channel attention. We have just use both of them. I mean, you can say we propose global channel attention over here. We have use the global channel attention or local channel attention just before the global channel attention, followed by something called as a fuzzy layer, right? So the different types of you can say membership functions we have used in case of fuzzy, right? Just to reduce the uncertainties that is present within the feature map, right? That was because this presence of these uncertainties also sometimes lead to misclassification. So just to tackle these problems, we have introduced a fuzzy layer, right? In case of the both local global channel attention and local global spatial attention. You can see over here. That was the main contribution. Also, there are other contributions which we have made recently. Like there's another paper which we have published recently, which is on glucoformer, the name which we have given, where we have used the transformer-based architectures for generalized glucose stage classification. Why the name is generalized glucose stage classification here is we have considered two data sets here. One data set we have used for training and testing, and the other data set we have only used for validating our model. That means the other data set is only used for checking the generalization performance of our model, right? So what we have observed that our model is really performing well, right? The model is really performing well compared to the other. Here are some of the results you can see, right? So the results comparison with some of the attention mechanisms, some of the visual results, right? Now Gartham results especially, which we have seen earlier. And here is some of the result comparisons with VIT models, especially Vision Transformer models, which are very, very popular nowadays, and see the results of our approach, especially. Here, the blue color indicates the best results, and the green color indicates the second best results, right? You can see over here. So our method is outperforming other even Vision Transformer based architectures, right? So that is one of the benefits we have. And as I mentioned, here is also, you can see the feature embeddings, right? Using TSNE. So TSNE, you might have heard about something called the PCA, right? That is used for dimensional reduction, and it's also TSNE is also similar to that. So it's basically used to represent the high dimensional features in a low dimensional. You can say you can just transform the high dimensional feature into its corresponding low dimension. And here it is, the dimension is 2, right? So that we can see the impact of this, the feature learning. We can say the feature learning capability of the model. So you can see over here, I mean, this is the kind of, you can say the feature embedding. So you can say different colors here represent different classes, right? So you can see the feature embeddings of the backbone architecture. And this is actually the feature embeddings after using the glucoformer, the transformer layer which we have proposed, right? So why the actually name is so called here glucoformer, and there is a dual domain, right? We also called it as a dual domain, right? It is really a very, very interesting concept which we have introduced. So this particular part which we have introduced is nothing but is a dual domain global transformer layer, right? So we are not only analyzing the features that in the spatial domain, we are also analyzing the features in the frequency domain, and that is why the name is so-called dual domain channel attention and dual domain spatial attention, right? So that means we are analyzing the features here in both the domain. One is spatial domain, which is the pixel domain, and the other one is the frequency domain. And this frequency domain analysis has been achieved through the first Fourier transform, and of course the inverse Fourier transform as well, right? So it is all the details of, if you just go through our mechanism, you will find the details of the mechanism. I mean, you can say the dual domain transformer layer which we have proposed, right? It's a really a very interesting concept, and very useful as well for solving few problems, right? I mean, for analyzing the images in both, you can say the domain, right? Spatial domain as well as the frequency domain. And as I mentioned here, the clusters are separate, well distinguishable, and that is how actually this transformer layer is trying to, right, separate the clusters of different classes, and hence performing well compared to the others one, right? So I was talking about, if you remember, the generalization performance. The performance, if you look at by our approach compared to the other approaches, it was like so our approach could able to achieve 86.85 accuracy, and there's F1 score, there's a area under the curve, all these values are given here, right? So this was the accuracy on the data set, right, which is known as SDB1. When we used our architecture, which is already trained on SDB1 dataset, on a different dataset, right, which is RIM1 R1 dataset, the performance suddenly drops. You can see the performance suddenly drops, and the accuracy is something 70% only. So previously, its accuracy was 86. So now, when it is applied on a on-scene dataset, on a new dataset collected in from different demographic regions using different imaging devices, the accuracy suddenly drops from 86 to 70, and there could be multiple reasons why the accuracy dropped, right? Yes, of course, and this is of course the future goal, that how to all right, improve the generalization performance of a model, right? So this is a common thing nowadays. If you submit your article to good journals or to top tier conferences, so they may ask you for the right generalization performance report, which is very, very important, right? So you can see, but compared to the other approaches, other best approaches, our model is still giving better performance, better generalization performance, although it is not close to 86% whatever we have got during training and all. Fine. So here is another contribution actually, which you can go through. And there are also a couple of other contributions which we have made over the years. If you want, you can just go through our profile and where you will get all the details of our paper and all. Fine. So now let us go back to our discussion and see some of the other things, right? So yeah, next is okay. I think I've only discussed about the classification. One is binary classification and one is again multi-class classification, like multi-stage classification, right? But there is something called as optic disk and optic COP segmentation. People have done also it individually. And if you want, you can also, you can individually highlight the disk, you can individually highlight the COP region, you can individually highlight the disk region, and you can then combine them. But if you want, you can also simultaneously solve the problem, which is pretty tricky, task, right? So, how the output will look like is something like this. This is what even this is very, very important, right? To detect glaucoma and all. So how to do this and all? Fine. You can see over here, this is the input image, and this is the optic cop, the small one, the yellow one. The yellow region is optic cop, and the outer one is optic disc, right? So this is actually the optic cop region, and this is the optic disc region. And these are some of the results of one approach, especially which is known as RFNet. Sorry, this is RFNet, and this is known as region focus network for joint optic disc and COP segmentation. I've taken from a paper from AAAI 2020, right? So this is the results of this RFNet is a proposed one, proposed by some of the others. So these are the results of the unit architecture which we have discussed, right? The unit architecture we have already discussed. We'll see also its demonstration tomorrow, right? Of unit architecture and all. You can see the results that unit, right, could able to give. It's not that accurate, not close to, although it is, of course, it is giving, but the boundaries are not precise and not giving very close result, right? Respect to the ground truth provided by the ophthalmologist. The kind of architecture that have been proposed in AAAI 2020, right? Region Force network is really giving better performance compared to the UNET and other standard architectures like MASC, RCNN, and all. This is another problem statement, right? People have done a lot of work on this optic cop and disk segmentation. You can just go through the literature if you are really interested, and you can also identify the research gap in this particular field. Now we will talk about another case study, which is diabetic retinopathy. So we've seen one case study on glaucoma detection, right? And now we will see something called as a case study on diabetic retinopathy. Again, there could be multiple types of tasks that could be solved on this particular statement, like binary, multi-class, right, which is known as diabetic retinopathy grading. Right? There could be different grades which you can consider on diabetic retinopathy, right? And that is something called as multi-lesson segmentation. Multi-lesson segmentation, right? So there could be, because there could be different lesions, right? That this diabetic retinopathy may cause. We'll see one by one, and then we will try to also segment all those things, right? Using deep learning algorithms, of course. We have already discussed all these things. We've discussed the classification-based architectures. We've discussed, the architectures which can also be used to solve multi-class classification problem. We've also discussed the architectures that can be used to solve segmentation task. And here now we are actually interested in solving particular task, which is nothing but diabetic retinopathy grading or diabetic retinopathy, multi-lesion segmentation and all. Diabetic retinopathy, as I mentioned, the most common sight-threatening medical conditions caused due to retinal microvascular changes triggered by diabetes. Right? So it mostly affects the working age population across the globe, and it also leads to gradual changes in the vascular structure, right, and resulting in certain abnormalities known as microaneurysm, hemorrhages, and exudates. And exudates again are of two types: soft exudate and hard exudates. Right. So if you look at the statistics, it is really surprising, right? And according to the International Diabetes Federation, according to the International Diabetes Federation, so what they're saying that the global number of individuals affected with diabetes is 425 million now, and it may rise to 693 million by 2045. These are the numbers, right, of the patients like to be affected by the diabetes. It is for the diabetes. 1 out of 3 individuals who are suffering from diabetes is estimated to have some form of diabetic retinopathy. That is why diabetes patients are always recommended to go for regular eye checkup. That's what you know, right? And 1 out of 10 diabetes patients is prone to vision threatening DR. So 1 out of 3 is estimated to have some form of diabetic retinopathy, and 1 out of 10 is prone to vision-threatening diabetic retinopathy. So then, how it is being detected? How this, now we can say how this diabetic retinopathy is being detected or diagnosed by the ophthalmologist. So it is being diagnosed with the help of course, retinal fundus images, but by looking at certain biomarkers, or you can say certain features, clinical features, right? So what are they? Those are like microaneurysms, I've already shown you, hemorrhages, soft exudates, and hard exudates. Let us also see with one example of the fundus image, all those lesions, right? You can see this is the whole fundus image. Here is the optic cuff, here is the optic disc. I'm not interested in this for this particular disease right now, right? And we are also not interested in vessels. We're not interested in fovea. We're interested in actually these 4 lesions. One is hemorrhage, one is microaneurysms. Very, very difficult to identify microaneurysms because it has same textures with the corresponding tissues. It has also the color distributions very similar to the background. So sometimes these kind of microaneurysms are missed by the ophthalmologist. And we need to identify those regions, right? Because this presence of these kind of lesions, right, leads to something known as diabetic retinopathy. So, there is something called as hard exudates here, right, which is a little bit easier to identify because the intensity values or the color values is something very prominent here compared to the background. Here is also the presence of, you can see, other hard exudates. Soft exudates are again a bit difficult one to identify, right? So these are the 4 lesions, or you can say the biomarkers, or you can say the clinical features which are required to identify something what is known as diabetic retinopathy diagnosis and all. And sometimes, as I mentioned, it is very, very difficult for the ophthalmologist to get all these details and all. Fine. So now, again, as I mentioned, the problem statement of diabetic retinopathy can be categorized into different types. One is like diabetic retinopathy grading. Given a set of images, your task is to say whether the diabetic retinopathy is there or not. And again, whether it is grade 1, grade 2, grade 3, or like there are different types of gradings we have in diabetic retinopathy that could be done. So we have also done some work on diabetic retinopathy grading, right? Where we have proposed some different types of, we can say attention mechanisms, which is really very, very important in this case. So I can show you that work of which we have just now. This paper has recently been accepted in IEEE transaction on instrumentations and measurement, right? And here you can see, I mean, basically what we have done here is we have proposed a multi-weighted multi-dimensional weighted attention model we can see over here, right? So we are considering 1D attention based weights, 2D attention based weights, and as well as 3D attention based weights, right? And we were trying to share important informations along different dimensions, right? I mean, both the local dependencies as well as the global dependencies of the features with the help of these three different, attention mechanisms, right, which we are considering simultaneously to capture all those informations. And we have, this is the whole idea behind, you can say, the development of this particular architecture, which is known as multi-dimensional weighted attention network. And we have used here, we have, I think, considered two different data sets to validate this approach. And here are some of the results on different data sets with different backbones, you can say, attention mechanisms with the backbones with the proposed attention mechanism. Here's the comparison. Here's some of the results of the ablation studies. Is there a need of three-dimensional, weighted attention and all? Because we have taken 1D, 2D, and 3D, so we must have to also discuss. I mean, you can say, prove that yes, all these components are really vital for us, and that is evident from these results that yes, when all these attentions, right, are combined together, that only gives better performance, and there's an improvement of 2.91% of accuracy if we are using all these three attention blocks. And if you are individually choosing one, so then you can see the improvements, right, in terms of accuracy and all. So a couple of other results were also, I mean, you will also find, and here are some of the visualization results. You can see, right, how our model could able to identify the important regions like hemorrhages and all, but how actually only the baseline models could not able to identify the salient regions that is present in this images and all. So that was the main actually motivation, that how to use or how to capture the dependencies locally as well as globally with the help of different types of attention mechanisms, right? And this is the proposed attention mechanism which we have, right? You can say published, fine. If you want, you can also go through this and you can get the details about it, and you can also interact with us, or if you can also, if you're having any doubts or if you need the code and all, you can send a request to us and we'll definitely share the code with you, right? So that is one of the thing. And there are also a couple of work which we have made on this is on actually diabetic retinopathy grading, right? So that's what I was actually interested in showing to you. So you can see over here, so because there are different types of diabetic retinopathy gradings. We have like mild diabetic retinopathy, moderate, severe, and proliferative and all. And the goal is here is it's like a 5-class classification task, right? So this is a grading task again, right? So, but as I mentioned that yes, there could be also problem statement on segmentation where your job would be, you can say, highlighting these regions, which is a pretty difficult task, right? Highlighting the regions where there are lesions like microaneurysm, hemorrhage, soft exudate, and hard exudate. So this is what is the most important thing, right? Even the most challenging part where you need to highlight these regions. So people started working, solving this problem as an individual segmentation problem with respect to different lessons, like how to design a model to segment hemorrhage, how to design a model to segment microaneurysm, soft oxidate, and how to design independent models, right? 4 independent models are required. 4 models are required to identify all these regions. But the major challenge is, can we have a single model to simultaneously detect all these regions, which is really a difficult task. And the current trend is actually towards designing a single model, right? Ultimately, we must have a single model which can be deployed and which can also have the capability to identify, or you can say highlight, all these regions, right? So what we have done is here, you can see, I mean, this is what actually we want. So these are like, this is a particular input image. This is like for microaneurysm. This is like for hemorrhage, the second one. The third one is for soft exudate. And the fourth one is for the hard exudate. And this one is not of our interest, right? So these are like hard exudates. You can see over here, these dark yellow color things are like, and these are like soft exudates, you can see. So we have already seen this, right, earlier. So here is a soft excluded also, right? So it is very, very difficult to actually sometimes identify all these things. As you can see, sometimes, it is not actually in the form of, you can say, a cluster or a particular regions, because the regions are, sometimes one region may contain even 2 pixels or 1 pixel. You need to also identify this. This is nothing but, let's say, microorganism. It's a very, very difficult task, right? So it's one of the tough, challenging tasks in medical imaging domain, that how to, solve this multi-lesion, right, diabetic retinopathy segmentation task. So, here is one of the results of the leaderboard. You can say, there was a challenge on diabetic retinopathy, right? And that was on 2020. And here are the winners of, you can see the team name of the winners, right? For this microorganism segmentation, you can see this table contains 4 different rows. These rows actually indicates here 4 different individual segmentation tasks we have. And here is the winner for each of the tasks. Here's the winner, you can see. The performance, if you look at in case of hard excluded, which is pretty easy to identify, I already told, is really high, the AUPR value. But in case of microorganism, it is very, very difficult. So that's why the value is really low. And one interesting thing you can observe over here, the winner, all the winners and all these runners up, right, approaches here, uses either unit or some sort of convolutional neural network based architectures, right? So that is actually what is really interesting here, that almost all the approaches you can see over here is either based on convolutional neural network or encoder decoder convolutional neural network, or of course is based on this unit architecture. That is really interesting, and that actually motivates now everyone to work on this kind of architectures, which is really popular. Here is one scenario, right, of you can say one sample image, right, which I have taken from one of the data sets available, right? Probably DDR. I still don't remember the data set name. Probably IDRID or IDRID. This is an Indian data set, or probably either from IDRID or from DDR, right? Okay. So here you can see, if you can see here, this is actually the input image, and this is the ground truth. Because in case of, we're talking about segmentation, right? We're not talking about the grading and all, right? So here is actually what is known as the input image, and this is the ground truth. You see, the annotation of this image is really a time-consuming process, right? So that ophthalmologist has to sit and annotate the image like this. Generally, we can have some supervised learning approach like deep learning based or unit based architectures to solve this problem, right? So this is going to be X for us, this is going to be Y for us, which is a mask or a ground truth. And then we will try to find out the relationship between X and Y, either using unit or using any other advanced architectures. That is fine, right? So, but if you look at here, sometimes here we are representing all the lesions in 4 different colors, like red, green, blue, and pink. The red basically denotes here the hard exudates, which is really visible over here. As I already mentioned, this dark yellow color, right, points. And hemorrhages are here only. You can see over here, these are like hemorrhages. Right? This is one of the hemorrhages, and here also there are a lot of hemorrhages. Right? And there are also small hemorrhages you will find, which is very difficult to identify through the naked eye. Right? And these microaneurysms, as I mentioned, this is blue in color. Microaneurysms, you can see over here, sometimes it is also a single point, and it's very difficult to identify. But your task is to actually simultaneously detect all those things, right? Which is even more difficult. That means, as we all know, that yes, it can be casted as a semantic segmentation task where every pixel is going to be classified into 5 different classes. If I'm right, we have already discussed why 5, right? Because we're including the background as well. So either it will go to background class, or excluded hard excluded class, or soft excluded class, or microorganism class, or you can say hemorrhage class, right? So every pixel has to be classified either into these 5 categories. So this is the task actually, right? It's a very challenging task, right? And very less amount of work has been done on this particular field because of its you can say complexity of the problem itself. And here is some of the results which we have obtained using our proposed approach. Sorry, I'm not able to show you the approach and all because still it is under consideration, right, in somewhere. So the kind of architecture which we have published is something different. It's a lightweight one and something very different from these state-of-the-art architectures. And it is compared with the very popular unit architecture, dense unit, unit plus plus. I think we have discussed about all these architectures yesterday, right? And also architectures like PMCNet, very popular architectures, HSC DR network, right? You can see what I'm trying to show here is this is the input image and this is the ground truth image provided by the ophthalmologist. And now if you look at, let's say this particular region, right? This particular region, if you look at here, and now you look at the output produced by different architectures and our architecture, which is pretty close to the original, I mean the ground truth, what I can say, right? You can see the boundaries are sharp, precise, and even the size is almost precise, right? It's very close to the ground truth. But if you look at the other approaches, if you look at, it is something very different. If you look at other approaches, it is something very different, right? So you won't find such kind of precise boundaries in case of other cases, right? Okay. So here are also some of the results. With here, even it is very typical. As I mentioned, it is a really challenging one, right? If you look at this particular image, and here is the particular ground truth one, right? Of the corresponding to this particular input image, fundus image, and now you can also look at, let's say, this particular part, right? And now we look at this part. This is a part which is representing actually the hemorrhages over here, right? Fine. You can see this particular part here, right? In the ground truth, and this particular part in our case is very close. But now we look at other parts. Look at the results obtained by the other architectures. It's something very different, something very different from the others, right? From this, something different, something the unit is could not able to even identify this particular regions properly, right? So that is, I mean, how you need to come up with some new ideas, right, for developing this segmentation approaches to deal with this kind of problems, especially where the lesions are very small and the lesions vary rapidly in terms of size and shape. So how to come up with some ideas to deal with this? You need to go through the literature and identify. I mean, couple of things, right? They are here, right, which we have proposed, and because it is very difficult to get this kind of results, right, compared to others. So that's one of the. You can also look at this particular region, right? You can see this particular region over here. This is the ground truth provided by the ophthalmologist, and look at the results obtained by the other approaches. You look at here, look at this one. It's very close to this ground truth, right? So very interesting task as well, right? And initially, what you can do is you can just choose some of these architectures like UNet, DenseNet, and UNet plus plus architecture, whatever we have discussed, right? All are available, and you can just fine tune on your data, and you can just get the outputs and all, and then you can see what are the problems these architectures are facing and how to overcome these kind of problems, right? And then only you can come up with some new ideas and all. Fine. Let us also talk about some of the key challenges which we have whenever we are facing or whenever we are solving some problems. We usually face actually these kind of challenges, right? And how to tackle all those challenges and all. So one by one, right? These are all very important points in medical imaging domain, not only in the field of fundus imaging, but also in the field of medical imaging, right? We can consider all these problems are like challenges for us and how to deal with this. There are some solutions also which I've written over here, but if you want, you can also explore a few more solutions, right? And those are like very important topics nowadays. People are focusing on solving those kind of key challenges in the domain of medical imaging. So what we have is always large, lack of large training data sets. We don't have much amount of training data sets. That is what is the problem which we always face while dealing with this kind of problem, right? So how to deal with this kind of problem? I already mentioned transfer learning also helps us to some extent. Data augmentation also helps us to some extent. If you want, you can also go for generative models to generate some synthetic images and again integrate with the training set so that the training set size will be bigger. And then you can train the whole model, right, with the help of the synthetic as well as the original images which you have. Annotation labeling, as I already mentioned, that annotation and labeling of the medical images is very difficult task. I've shown you some of the segmentation task, right? So annotation of these images are a bit difficult, right? if I ask you to grade or annotate this image in the form of a grade or in the form of a class, it is very easy, right, to say that this is mild dr. So this is how we can you can say grade one particular image in case of classification task. But in case of segmentation task, we need actually the whole mask, which is really a time consuming and difficult task, right? So for a task like segmentation and all, it is really difficult to get the annotated images. So how to solve the problem, because we don't have that number of ophthalmologists to what I can say to annotate all those high number of medical images that are generated using fundus cameras and all. So yes, I mean, of course we must have some number of samples for which annotation should be there, and then using some sort of algorithms you can generate the pseudo levels, like you can explore what do you mean by semi-supervised learning and all. High resolution images are, because most of the times the medical images are high resolution in nature, right? So if you consider WSI image, whole slide image, even these images like fundus images are like having high resolutions, and working with those high resolution images directly is sometimes very difficult. If you are planning to use those images, right, through if you want to planning to pass through those images through densinet, resonate, probably alexnet and all, so you need to first downsample the image to have the compatibility, right? So because of the compatibility, we need to first downscale the image from, let's say, 1024 to 1024 to 224 cross 224. That's what you know, right? You need to first downscale it. And then only you can pass it to the CNN, pre-trained CNN architecture like AlexNet and all. But while downsampling or downscaling this particular high resolution image to the image having size 224 cross 224, there's a possibility that you may lose some of the important information, right? So how to tackle all those problems, right? How to tackle actually all these problems? So you can just tackle these problems just by using some patch-based models, right? So you can think of using exploring even vision transformer kind of models, which is usually used right, which usually follows splitting of the patches, then directly work with the patches and all. Fine. So there are also a couple of approaches available. Those are patch based. That is also what you can do. Handling class imbalance issue. As I mentioned, class imbalance is always a problem, because whenever you are solving even a multi-class classification problem at that time, if there are, let's say, 3 classes, let's say for example, one is normal, one is early stage glaucoma, and one is advanced stage glaucoma, right? So you will find most of the time, let's say 1,000 samples from here, maybe it's, for 400 samples from here, and sometimes even 50 samples from here. So this data set is purely imbalanced, right? And you are planning to develop a model, right, where develop a model using these data sets. So it is, so if you train the model, right, without looking at this class imbalance issues and all, the model will be biased towards this class, because this is the majority class and these are the minority classes we have. We don't want that, right? Because a model should not be biased towards this class, right? So it should give equal importance to each of the class. Then how to deal with this kind of issues? So random sampling techniques like oversampling, undersampling techniques we have, which can help us to some extent. You can also, if you want, explore the general purpose network models to generate the synthetic images and make it to 1,000 or sometimes even 500, so that the class imbalance issue will be reduced further. Demand of huge amount of parameters, a very, very important thing. There are few models, right, which demand huge amount of parameters like vision transformers, and some of the architectures we have, which takes millions of the parameters. And you know that if the model is having huge number of parameters, then the computational you can say the training time is going to be really high, because again because of the number of computations which we have. And in that case, it will be even difficult to, what I can say, deploy those kind of algorithms, right? Fine. And there are also a couple of other things which I will discuss in the tomorrow sessions. I mean here, but I will right now take you to the demonstration session. Right, here are some of the points which I would like to discuss in the tomorrow session. But demand high amount of parameters, like I mean, we can think of designing lightweight models instead of using the heavy models, right, which takes a lot of parameters. We can think of using lightweight models. You can prune the models. There are multiple ways to use right now the heavy models and or to transfer the knowledge from the heavy model to the lightweight models, right? I don't know how many of you have heard about something called as knowledge distillation. Knowledge distillation is a very, very important concept, right? Where there will be two different networks. One network is treated as a teacher. One network is treated as a student. This is a heavy model, and this is a lightweight model. We want to, right, give power or distill the knowledge from the teacher to the student model, right? So if you directly work with the student model, which is lightweight, you may not get good result. But if you are transforming the knowledge from these teachers to the student, you are going to get, right, better result. That is what is the all about something called as knowledge distillation. And those kind of also, concept can be introduced here to deal with, right, this heavy, to work with these heavy models, right? So, even the heavy models cannot be deployed, right, in the resource constrained environments. So we need actually the lightweight models to be easily deployed in resource constrained environments. But we don't want to design the lightweight models here. In this case, we have the heavyweight models, which has learned a diverse set of features from the images and all, and we want to distill the knowledge from or transfer the knowledge from the teacher model to the student model. Really, really interesting concept, right? And the other parts I will discuss later on. Let me directly take you to the hands, and I'll show you some demonstrations especially, right, on basically transfer learning, which I discussed, and another one is attention mechanism, which also we discussed, right? So before that, we must have actually idea on the how to implement or how to design an implementation setup, how to design an implementation setup for solving classification task or segmentation task, whatever may be the task. For simplicity, I'm considering a classification task here. Let's say a classification task which I'm considering. And there are, let's say, chest x-rays I'm considering, chest x-ray images. And I want to classify the chest x-ray images either into three categories: into normal category, that means healthy category, or pneumonia, or COVID-19. So given an image, my model should, right, classify the image either into this category or this category or this category. This is what I want. So what is the learning set of here? So you'll be given a data set, of course, right? Set of xi's and yi's, pair of xi and yi's, right? Where I, let's say, varies from 1 to n, and n is total number of images, just x-ray images we have. What is x? The input images, or you can say the images. What is yi? The labels, like normal, pneumonia, and COVID-19 and all. What is the first task? This is given to us. Given a data set, right? What we do is we split the data set into train and test set. Sometimes this is also given to us, right? Sometimes, right, the data set contains, right, different folders. You can say different sets, training and testing. So we need not to think about splitting, how to split the data set and all at that time. So what we can do is we can simply use the train set to train the model or to build the model, and we can use the test set to evaluate the model. That is what we know, right? And if the model is performing well on the train set and test set, then it is, of course, right? We can say the model is really performing well. Then we can, right, think of, you can say using that model in real-time scenarios and all. That is what we know. But if it is, let's say, not given, if only data set is given, and you don't have any images, let's say, sorry, you don't have any splitting criteria in the data set, so what you can do, you have to manually split the data set into train set and test set. What we know that to develop any model, whether it is machine learning and deep learning. So we need basically two stages. One is training stage and one is testing phase. We have also one more phase which is known as validation. Very powerful phase also, right? We cannot even exclude that validation phase. But now I'm skipping that particular phase, that is validation. But what we should have always is train, validation, and test, right? Fine. But most of the time, what we need is these two are mandatory, right? Train and test. So we need to first split the data set into training and testing. Let's say your image, your data set contains, sorry, 1,000 samples from this category. Let's say 700 samples from this category and 300 or 400 samples from this category. Let's say 300 samples from this category. And now I want to apply the splitting approach over here. Random split approach, the percentage split approach. I think that's what you also know, right? So can you tell me that how can I split this data set which contains here n is equal to 2000? It is 1,000 plus 700 plus 300 is nothing but 2000. Now can you tell me how to split this? How can I split this data set into train set and test set? Do you have any idea? Yes. Do you have any idea how to split the data set into train and test? You can write your your answer in the chat box. Yes. Do you have any idea on this? I hope I'm audible to all of you. Okay, thank you. It's a very small thing, right? If you have done some course, if you have done some course on, machine learning, probably artificial intelligence, computational intelligence, subcomputing, and all. So you might have heard about these two terms like train set, test set, or training and testing, right? How to split that data set into training and testing? Okay, I could see some of the answers. So thank you, Dr. Akash, Dr. Basundra, Manish Patel, 70, 30, 80, 20, usually. Okay. So that means there is no such, hard and fast rule here, right? To either, to take 80, 20 or 70, 30. But what we know that, yes, these are the common ratio which we follow, right? This even validation set can be, okay, let me check validation. Yeah. That's what I discussed, right? That's what I discussed that I'm right now considering train and test. But if you want, you can also take, validation as a separate set here. But that is again totally different from test set, right? So validation is always extracted from the train set. You can also have a validation set here. Very important, right? Validation set, right? So now right now we're only focusing on training and testing, right? Let's say I've chosen 70-30, right? I've chosen the solutions provided by Dr. Monish Patel. It is 70-30. Now, what I know that if I apply 70, that means I want to keep 70% of the samples out of 2000 samples, which is nothing but 1400 samples for training, and the rest of the 600 samples, right, for testing. But now there is a question here. So how to choose or from which class I should take, right? Or how much samples, right, I have to take from each of the class to make it 1400. because it's random. This is a random percentage split. You have to follow this random procedure here. Random percentage split is actually the procedure to be followed over here. That means you are randomly choosing 1,400 samples out of the 2,000 samples. Is this the right way to do this? Directly choosing randomly, right, from these 2,000 samples? 1,400 samples, you need to choose randomly from these 2,000 samples. Is this the right way to do or to prepare the training set? Or will there be any problem here? Yes, of course, there will be some problems, right? Yes, class imbalance will be there. Absolutely correct, right? Because the class imbalance, it means that what us is saying that if I choose 1,400 samples, there is a possibility that all the 1,400 samples may come from the normal in pneumonia. There may not be much number of samples or no samples from COVID-19, right? So then what is the solution here? The solution is here is nothing but stratified. Stratified is the solution. Stratifiers will ensure, right? Will make sure that we are choosing same distributions, right? Or equal distributions from each of the class. So what does it mean? Instead of taking 1,400 samples from the 2,000 samples, what you will do, you will apply 70%. You will not apply 70% on 2,000. Rather, you will apply 70% on each of the class, right? So that will make sure that you will be having samples, right, from each of the class, and the distributions is same for each of the class. So that means here I will take 700 samples from the first class. I will take, that means out of this 1,400, 700 should come from the first class, plus probably 490 from the second class, and 210 from the 210 from the third class. Now this will form the trend set, right? So you should not actually forget this kind of thing while splitting the data set. We need to remember that stratified is the solution here, which we should always apply if we are dealing with a multi-class classification task, right? So always we should apply the 70% on each class rather than the whole sample or rather than the whole data set. So now we are having 1,400 samples for training, 600 times. The rest of the 600 samples, that means 300 from here, 110 from here, 90 from here, right? So that all 600 samples, 200 from here, I think, 210 from here, and 90 from here will go for the testing set. Now there is something called as a validation set. And validation set is very, very important to overcome certain issues, even to decide the optimal parameters of the model, right? This validation set is sometimes very, very useful even to, right, avoid something called as overfitting issues. By looking at this validation set, you can also avoid overfitting issues. You can also decide, right, the optimal parameters of the model. These are like, again, kind of test set, but it's a part of the training, right? So validation set. So every time you need to train the model and check the validation performance. If the training performance is good and the validation performance is good, that means this model is doing really well. You can continue your model for training. And if your model training, if the training performance is good and the validation performance is not good, then you have to stop the training process. That is what is known as early stopping. And early stopping is one of the criteria, right? Which is, or we can say one of the regularization technique, which is used to overcome the problem of overfitting. So validation is really, very, very important. And how to get this validation? So to get this validation, you can apply either a percentage split. One more time, you can apply 70-30 or 80-20 over here, right? Again, 80 for training and 20 for validation, or you can also apply a fold cross validation technique over here. A-fold cross-validation technique, right, to get a validation set. I mean, usually the K value is 5 or 10. So where every time you'll be having 4 sets or 4 folds that will go for training and 1 set will go for validation. I hope you all know what is K-fold cross-validation and all. This is a part of, again, in the traditional machine learning, right, and all. Okay. that is not the part of our discussion, right? So I mean, our main goal was to how to split the data set into train, validation, and test set. We did it using this approach. There are also other approaches, but this is the simplest approach we followed. After we have this training set and test set, we will use this training and validation, right, or train set to design the model. Then we will design the model, right? Of course, we'll design the model. And we are right now talking about this CNN model, right? We'll design the CNN model, or we can also apply the transfer learning concept to solve the problem, right? So this is what is the architecture which we are trying to design to solve our problem. And our CNN architecture should have 3 neurons or 3 nodes in the output layer. That is what we need to fix, because we have 3 number of classes, and every node is going to give us a probability value. That means we are going to use a softmax activation function. Once you will design the model, like how many convolutional layers will be there, pooling layer followed by, right, different types of activations and all, fine. So then what you can decide is different hyperparameters, which is very, very important. Hyperparameters we need to train the models, right? That also we can initialize here. That also we need to initialize, like learning rate, the epochs, how many epochs we need, what should be the batch size, very, very important. I mean, while computing the error, we are not looking at all the samples, or we are not computing the error one by one, right? So there are various ways actually to compute the errors and to train the model, right? One is like after passing each sample, you can find out the loss here and then back propagate the loss. This is one approach, right? And then you need to again pass the second sample, get the loss, back propagate, and then this. That is actually sequential learning. Sometimes people call it stochastic learning as well. And there is something called edge. There are a lot of concepts, right, which we cannot cover. And there is something called as a mini batch. There's a batch learning where you will pass all the samples. You will accommodate loss 1, loss 2, and let's say there are n number of samples. You'll be having n number of losses. You will combine them together, and then you will back propagate, right? But you need to wait, right, for all the samples, then compute the error, then only you can back propagate and you can solve the problem, or you can optimize the model and all. And mini batch is what is the most popular one. It is just in between, right? It is having the advantage of both sequential as well as batch. So you need to first divide the number of samples, let's say n number of samples, into different number of batches, batch 1, batch 2, and so on up to, let's say small n number of batches. And you will pass this many number of samples to compute the error, and then you back propagate it, right? That is what is about mini batch, which is very, very popular. And that is what you need to also decide how many, and this batch size again depends on, the GPU capabilities which you have and all, right? At the same time, we need to also decide the most important thing, what should be the loss function, like cross entropy, which we all know, and what should be the optimizer, like the stochastic gradient descent. It could be Adam, very, very popular. Maybe the latest one, Adam W. It could be anything. You need to also decide all these things, right? And then once all these hyperparameters are initialized, you will train the model. Then the training process starts. We call it as a compilation process also, right? So then you can just train the model with all these hyperparameters, initializations and all. So once the training is done, right, for this many number of epochs and all, so then it is your task to save the model and then evaluate the model on test set. Because it is a classification task, you can compute the confusion matrix, right? So this is one of the, you can say the implementation steps to be followed to solve classification task. One more thing, what we can do here is, I mean, if you are trying to solve, let's say if you are trying to, what I can say, use this transfer learning as a concept to solve the problem. So instead of designing the model, what we can do here is you can load the model, whatever is available with us. In this case, you can load a pre-trained model I'll show you the code also. Load a pre-trained model, right? Load a pre-trained model. And then what do we know that we need to remove the last layer. Why? Because the last layer usually contains 1,000 nodes because it was trained on ImageNet dataset. Replace a new layer, then decide the number of layers to be fine-tuned. I mean, how many layers you want to fine-tune, right? That all depends upon the size of the data set we have and whether the target task and the source task both are similar or not, right? And then again, you need to, if you want to fine tune it, then you need to again decide the hyperparameter, right? And then you can fine tune the model. Once the fine tuning is complete, you can evaluate the model, then the job will be done, right? I think we are running out of the time. The time is already 8 o'clock. Let me show you the demonstrations of it, especially these two things, right? Otherwise, I'll show the demonstrations and attention tomorrow, right? Let us look at the first one. Yeah, this one. Choosing actually, Google Colab is a platform, right? Where I need not to even install all the libraries, whatever is required, right? It's already there. So I'm choosing Google Colab as a platform, easy, where I can also get the GPU facilities and all, right? If you want, you can also choose Kaggle as another platform to solve this. It's up to you. And there are also multiple, tools we have implementing the deep learning, especially the convolutional neural network models. One is like TensorFlow, and one is PyTorch, as I mentioned, right? So I think here I've chosen TensorFlow and Keras as the tools for implementing this. And if you are interested in PyTorch, you can also think of, just writing the code using other language. I mean, both. I mean, this you can say TensorFlow and like PyTorch are such tools developed by Google and Meta, right? But for the same purpose, if you want, you can also design the approach using PyTorch, right? It's up to you what you want to do, right? So always we need to deal with the tensors, and that's why they have just given the name as TensorFlow, right? So the tensor could be sometimes 1D, 2D, 3D, even beyond that, right? That's what you know, right? That's the output of the each convolutional layer. That's the feature map. Fine. So let us look at the code and try to understand. So whatever we have discussed, right, and same way whether we have implemented or not, right? So initially, this mounting is these are some of the codes which are required actually for mounting with the Google Drive, because you want to, if you want to solve the problem, or if you want to write the code on the Google Colab, you need to first load the data set in the Google Drive so that the mounting will be easier. You can directly get the data from the Google Drive, right? So here is some sort of code for this, right? And then there are certain libraries we want, right? The libraries may contain like NumPy is very, very important to deal with the tensors, especially high dimensional arrays, 2-dimensional arrays, and 3-dimensional arrays and all. We also need to plot something, right? Sometimes maybe the convergence curve and like this. So for that we need matplotlib. These are all libraries which are very, very important, and Python supports all these libraries. TensorFlow is very important to design the convolutional neural network. All these things. Please go through all these libraries which are important for this. And CV2 is one of the most important libraries, which is known as OpenCV libraries, important for taking input as images, so showing output as an image. And there are a lot of other image processing operations that can be done using this CV2 package or libraries, right? So here, fortunately, the data set people has already given, right? Already given the splitting, right? That means the train set and test set has already been splitted, right? I mean, it's already available. The data set is already available with two individual set, that is training and testing. We did not follow any train test split algorithm, right? We have also functions available, right? If you want, you can go through that. There's an option also for stratified. If you want, you can switch on the stratified one so that the distribution of each of the class is going to be same. Fine. And here are just some of the codes to load the data set from the directory, and how to visualize some of the random images that is available in the image. Sorry, in the data set, right? You can see over here, there's a IM read to read the image. There's a IM show function available in CV2 to actually what I can say, to display the image. This is how actually an image, chest X-ray image looks like, which which is from a certain category, right? There are 3 categories as I mentioned. And here we are preparing the train set and test set because it is available in the directory. So here, what we are trying to do here is we are initially resizing the image to 100 cross 100 because the initial size was really larger. So we have just resized it to 100 cross 100. We've decided the best size here. And also we are rescaling the image. It was originally from 0 to 255. And what we are trying to do here is we are making all the values from 0 to 1 as simply normalization and all, right? And this is where actually we have defined the CNN architecture, right, which contains 3 cross 3. You can see layers, convolutional layers, followed by ReLU, followed by max pooling. Again, 3 cross 3 with more number of filters, right? And finally, this is the last layer. After that, we have flattened because the output is still in the form of 3D feature map or 3D feature volume. Either you can apply a global average pooling over here. There are 2 approaches actually to make it 1D. Either global average pooling is one of the approach or flattening is one of the approach where you are actually converting a 3-dimensional matrix into a 1-dimensional vector, right? And at the end, you can see here the last dense layer. There is actually one more dense layer we have introduced here. But this is just to show you something, right? How to build this CNN architecture. There are layers already available with us. I mean, these functions are already available. Only you need to pass the parameters of that particular function, right? I mean, what do you want? What should be the kernel size or filter size? What should be the activation function? And what should be the input of this particular layer? And what should be the output of this particular layer? That is what you need to mention, right? And you see how easy it is, right? All are available as in the form of Keras layers, right? That is what you can do. And next. And then we have introduced a dense layer, which is a fully connected layer having 128 neurons. There is a dropout layer where you can drop out the neurons which are actually not important or not taking any decisions, right? So I mean, we are generally not removing any neurons. We are just making those connections off, which are not important and all, right? And finally, as I mentioned, you'll be having a softmax layer, which is a classification layer, and the number of neurons in this case is nothing but the total number of classes we have. It is 3. Here it is 3. And if you just summarize the model using a model.summary function, so what you will get is the output at every layer along with the number of parameters involved in that layer. So that is where actually you can identify that how many trainable parameters if you have. This is a very common thing now. You need to also write in your paper that how many parameters your model is having. So this is how actually you need to compute the parameters, right? And then, as I mentioned, we need to decide the hyperparameters to compile or to train the model. We need to decide the optimizer, the loss function. And there are a lot of other things which I have not mentioned over here, but you should mention over here the number of what should be the learning rate. And there are a lot of other things, right? You need to mention over here, like number of epochs, base size we've already discussed. And in the history here, we are trying to train the model. But here, actually, there is no validation set. That is why I have taken the test set as the validation, but you should not take this. Test set is not validation. Validation is something very different. Test set is something very different. We should not touch the test set. It is only used to validate it. It is only used to evaluate the model, right? So only because it is not available in this case, and I have also not done any splitting on the training set to get validation set. Just for, just to show you something I have taken here, but this is not correct, right? I should not take actually test set as the validation set. Just to show you something, I have taken this, right? And then once training is done, you can just evaluate the model on the test set, right? This should not happen actually. The test set is something very different, only used for the model evaluation purpose. Now I'll show you something, whatever we have discussed, maybe 2 days back, that is what is transfer learning, right? So in transfer learning, as I mentioned, all these things is going to be same. You need to mount with the drive. We need libraries, of course, whenever it is required. We need, because we are using certain functions, those who are available inside these libraries, we need to first call those libraries and all. And again, we are considering the same data set, which where the training set and test set is already available. And then, of course, we are trying to normalize the data. We are also trying to here use some sort of data augmentation approaches, which is really important, right? Data augmentation, you can either perform some affine transformations on the images to perform data augmentation. Fine. Here are some of the data augmentation approaches we have, and here are some of the images randomly, right? We have shown after applying the augmentations approach, right? How it looks like. And here's the main code. what is the main code? You need to first load the model, each model, pre-trained model, right? So here in this case, we have loaded the VGG16 model, and the weights are from the ImageNet. You know that VGGNet was trained on the ImageNet dataset, and here also we have mentioned include top is equal to false, and the input shape should be this. You need to decide actually what should be the input shape. So include top is equal to false means we are removing the top layers, the top fully connected layer. And then, right, we want to remove that because it contains 1,000 number of neurons, right? And then we want, what we want? Now we want to also introduce another layer which contains only 3 neurons, right? So what we did here is we initially, removed the top layer using this particular, parameter by making it false. And then we are adding here new top layers. No need to even add this layer, right? Either you can, what I can say, either you can add one layer, or if you want, you can add more number of layers. But we discussed that if you add more number of dense layer, the number of parameters are going to be high, right? So if you want, you can also ignore this one. You can only think of including a single dense layer, which is a fully connected layer having 3 neurons, and the output activation should be a softmax, which gives us the probability values, right? So if you just write, so base model is the, you can say base model is where actually the output of the VGG net lies, right? And then thereafter, there are two possibilities. Either you may flatten the output, or you can apply also global average filling. That's what I discussed, right? The functions are available. You need to only call the functions, right? And pass the input, right, to it, nothing else. And then finally, you will prepare the model, and then you need to decide that how many layers you want to train, whether you want to train the last layer or whether you want to train the whole model, right? So in this case, I want to only train the last layer, let's say. So what I will write here is layers.trainable is equal to false. If I'll make it true, that means I want to fine tune all the layers, whatever VGG is containing, right? That is what is actually, false here and true here, right? So true means I want to fine tune the whole model. False means I want to only fine tune the new layer, whatever I have introduced, the new layers. I'm especially the new top layers. It may be 1, it may be 2, it may be 3, the number of layers you have included, right? And then, so now your model is defined, right? But you have not designed your own model, and you are not going to train it from the scratch. Whether you are going to train or you are going to adjust the weights that have already been adjusted on this ImageNet dataset, right? And that is why it takes a lot of the less time, less computational resources, and gives also better performance. And here are some of the, you can say, hyperparameters I've decided what type of optimizer and loss function I should take. And then here is a convergence graph. You can see you can also run it for few more epochs to have the convergence better, to have a better convergence graph here, right? I've just, for simplicity, I've just taken 30 here. But if you want, you can also reduce the error values close to 0 you can get. And I have stopped the training process after 30 epochs. And then I have evaluated the model using the test samples. And I have got the output, that is the y pred probabilities. And there is a output which is already given, y true. Then I have finding out a correct matching between these two, then try to find out something called as the cross confusion matrix in between the predicted value and the true value. This is the kind of output which we have got on the test set, right? So almost all the COVID samples are correctly classified. The normal samples are sometimes misclassified to viral pneumonia, and there are also viral pneumonia, seven viral pneumonia samples are misclassified to normal, right? So this happens, right? So you can see there's improvement in the performance using what I can say is transfer learning, right? So, so if you require, then I will share also the code with you all, right? And the attention part I will discuss tomorrow, because I think the time is 8:16, right? So tomorrow I have a session. So I'll discuss, I'll show you the demonstrations on the attention mechanism which I discussed, as well as the demonstration on segmentation. And then I will discuss the topic, right, which has been assigned to me, which is a really interesting topic and very powerful topic also, known as how to detect colorectal cancer using cutting-edge AI technologies. So I'll stop here, and if you are having any queries, so you can write them in the chat box. I'll be happy to take a few questions.
Okay. Any question from the participants? If not, then thank you, Deepak sir. Possibly sir will be with us tomorrow as well. So means if you have any question, then maybe you can ask sir tomorrow also. So tomorrow participants, we have a class from 10. Okay. So tomorrow we have a 10 to 5 as a Saturday classes. Okay. And day after tomorrow, Sunday, again you have a second quiz. Okay. We have a last day tomorrow. And after that, on Sunday, we have a quiz for you. Okay. Thank you. Okay. Thank you. Thank you all of you. See you tomorrow again.